What specific problem does the proposed method aim to solve in the context of tokenization, and why is this problem significant for natural language processing?
The proposed method aims to solve the problem of finding optimal tokenizers that maximize the compression of a dataset while adhering to specific constraints, such as a maximum vocabulary size and a target number of symbols. This problem is significant for natural language processing (NLP) because effective tokenization directly impacts the performance of language models. A poor choice of tokenizer can lead to inefficiencies in training and inference, as well as degraded performance in downstream tasks. The paper demonstrates that both direct and bottom-up tokenization problems are nitrogen monophosphide complete, indicating that finding optimal solutions is computationally challenging. Consequently, the authors suggest focusing on approximate algorithms like byte-pair encoding (BPE) and unigram LM, which are more feasible in practice. By addressing the complexities of tokenization, the method contributes to improving the efficiency and effectiveness of NLP applications.
How does the proposed tokenization method work? Illustrate the main algorithm steps in detail, including how it defines vocabulary and computes compression.
The proposed tokenization method operates through two main approaches: direct tokenization and bottom-up tokenization. In direct tokenization, the algorithm defines a vocabulary, vocab, as a set of subwords that can be used to represent a character string. The objective function, objective func, is defined to maximize compression, specifically, objective func subwords equals subwords, which allows the algorithm to compute the optimal subword string, subwords, that is equivalent to the input character string, characters. This is achieved by selecting a vocabulary that maximally compresses the dataset, which is verified by checking if the total length of the compressed output meets the specified max symbols. In bottom-up tokenization, the method starts with a set of character strings and iteratively merges pairs of subwords to form new subwords, defined by a merge function, mergefunc. The sequence of merges is crucial, as it determines how the character strings are compressed. The algorithm computes the resulting string after each merge and checks if the total length of the compressed dataset is within the limit set by max symbols. Both methods are shown to be nitrogen monophosphide complete, indicating that finding the optimal tokenizer is computationally challenging, thus necessitating the use of approximate algorithms for practical applications.
Can you provide a simple and illustrative example to demonstrate the inner workings of the proposed algorithm, particularly focusing on how it encodes a character string into subword strings?
To illustrate the inner workings of the proposed algorithm, consider a character string cat. In the context of direct tokenization, we first define a vocabulary, for example, vocab equals CAT at. The tokenization function, tokenize, will then map the character string cat to an optimal subword string. Given our vocabulary, the function could encode cat as subwords equals CAT or alternatively as subwords equals at. The choice of encoding depends on the objective function, which in this case aims to maximize compression. If we consider the objective function, objective func subwords equals subwords, the encoding that results in fewer subwords, like using at, would be preferred, demonstrating how the algorithm efficiently compresses the input string into a subword representation. This example highlights the algorithm's ability to choose between different tokenization strategies based on the defined vocabulary and the objective of compression.
What are the primary theoretical or practical advantages of the proposed method compared to existing tokenization techniques like byte-pair encoding and unigram LM?
The primary theoretical advantage of the proposed method over existing tokenization techniques like byte-pair encoding (BPE) and unigram LM is its focus on finding optimal tokenizers that maximize compression, as demonstrated by the nitrogen monophosphide completeness proofs for both direct and bottom-up tokenization problems. While BPE and unigram LM are heuristic methods that provide approximate solutions, the proposed method aims to establish a more rigorous framework for evaluating tokenizers based on a defined objective function, specifically targeting compression efficiency. Practically, this means that the proposed method can lead to better compression outcomes, which in turn can enhance training and inference efficiency, improve downstream performance, and ensure fairer treatment of multilingual datasets. Additionally, the paper suggests that understanding the characteristics of a good tokenizer can inform the development of more effective approximate algorithms, potentially leading to advancements in tokenization strategies beyond the current heuristics. Overall, the proposed method provides a foundational theoretical basis that could guide future research and practical implementations in tokenization.
How was the proposed method validated, and what datasets or experimental setup were used to test its effectiveness? What metrics were employed to evaluate its performance?
The proposed method was validated through theoretical proofs of NP-completeness for both direct and bottom-up tokenization problems, rather than through empirical testing on specific datasets. The paper does not detail any experimental setup or datasets used for testing. Instead, it focuses on the theoretical framework and implications of the findings. The effectiveness of the tokenizers is evaluated based on their ability to maximize compression, with the objective function defined as objective func subwords equals vert subwords vert. This metric indicates that improved compression leads to more efficient training and inference, as well as better downstream performance. The paper emphasizes the need for approximate algorithms like BPE and unigram LM, suggesting that these methods are practical alternatives given the nitrogen monophosphide hardness of finding optimal tokenizers.
What were the specific results achieved with the proposed method, including any quantitative metrics that demonstrate its performance improvements over existing methods?
The paper primarily focuses on proving the nitrogen monophosphide completeness of various tokenization problems, particularly those aimed at maximizing text compression. While it does not provide specific quantitative metrics demonstrating performance improvements over existing methods like byte-pair encoding, BPE, or unigram LM, it emphasizes that these existing methods are approximate solutions and may not yield optimal tokenizers. The results imply that finding efficient algorithms for optimal tokenization is unlikely, suggesting that researchers should continue to rely on approximate methods. The paper also discusses the theoretical implications of improved compression, such as more efficient training and inference, and better downstream performance, although it does not quantify these improvements. Overall, the findings highlight the complexity of achieving optimal tokenization, while reinforcing the need for approximate algorithms in practical applications.